we have the wonderful opportunity to welcome Advait Jukar, who is coming to us from Yale University in New Haven, Connecticut, where it is now half past midnight, and we're awfully grateful for him to be up in the night together with some of his colleagues on the East Coast of the United States. Advait is a postdoc at Yale in the Yale Institute of Biospheric Studies and the Department of Anthropology. And he's been working on the Cevallic fauna for many years, 8 years plus. He got his bachelor's degree from Reed College, which is out western United States. And then he got his PhD and master's also from George Mason University in 2018. And his research has covered the evolution of life in many different ecosystems around the world. But tonight we're going to hear his analysis of the herbivores from the Cevallics. And I'm going to turn it over to Advait.
Thank you, Bob. All right. Did that work?
It's working, so you need to get into, there you go. Right now, it's beautiful.
It's full screen? All right, awesome. Thank you so much. And it's a great honor to be here presenting to all of you. Today, I'm going to be talking about Plio-Pleistocene faunal changes in the Indian subcontinent with special reference to the Cevallics and how that's linked to the assembly of the modern large herbivore guild. So I'm going to be focusing on the upper Cevallics, which is the Plio-Pleistocene part of the section. But the Cevallic group includes rocks which go all the way from the latest part of the Oligocene all the way up into the middle Pleistocene. And there are co-eval sections all across the northern part of the Indian subcontinent, in Nepal, in Balochistan, and in India. So just to give you a brief overview on where we are in time and space, the upper Cevallics consists of sediments which were laid down between about 3.5 to 4 million years ago, all the way up to about 500,000 years ago. The lower part of the upper Cevallics includes the upper Pliocene. The world was a lot warmer and wetter in the Pliocene. Sea levels were higher. And as we transition into the Pleistocene, things start to get a lot colder, a lot more seasonal. And with the onset of the glaciations in the northern hemisphere, a lot of water got trapped up at the poles, sea levels started to drop, and all of this facilitated the movement of animals around the old world and the new world. Most of the upper Cevallic localities can be found in a few places in India and Pakistan, at least the well-dated ones. They can be found in the Chandigarh region between the Yamuna and the Sutlej. They can be found near the city of Jammu, and in northeast Pakistan near the village of Tatrot in the Pabi Hills and on the Mangla Samwal anticline, and up in the Camelport Basin. The first fossils from the upper Cevallics were collected by English explorers back in the 1830s. William Erskine Baker, Henry Durand, Hugh Falconer, and Proby Cotley were all part of the East India Company, and they started to explore the hills between the Sutlej and the Yamuna, and they uncovered one of the largest caches of fossils that had ever been found back then. Just to give you a sense of where they were in relation to some of the other sites, they were down here between the Yamuna and the Sutlej. Subsequent explorations by the Geological Survey of India in the 1950s, most notably by William Theobald, and then by Guy Pilgrim in the 1910s and 20s, and famously by Barn Brown in 1922, expanded our view of Cevallic ecosystems to the Potwar Plateau. And more recently, in the 1960s, researchers from Punjab University in Chandigarh, like M.R. Sani and S.M. Khan, started to explore the Cevallic hills once more to the town of Chandigarh and Jammu. And along with MR science, there were new explorations by the Geological Survey of Pakistan, by the Harvard team, and by teams from various universities in Europe and Pakistan as well. And what all of these expeditions did is bring about this huge assemblage of fossil mammals going back about 4 million years, and it's remarkably well preserved. It's remarkably complete. The best preserved fossils belong to 3 orders of large herbivores. They're the artiodactyls, or the even-toed ungulates, animals like Bosicutafrons, which is this extremely long-horned bovid, buffaloes like Hemibos, gazelles like Gazella lidecari. This is from Barnum Brown's collection at the American Museum. Damalops paleoindicus, which is an elcelophene. These elcelophines today are found in Africa. You have deer like Cervus punjabiensis, camels, even enormous strange giraffes like Cevatherium, which had extremely long ossicones, which made it look kind of like a moose. You had a extremely high diversity of suids, including a suid called Colpocaris, had long canines. You had anthracotheres like Merycopotamus and hippos like Hexaprotodon. Now, coming to the second order of mammals that are particularly well preserved in the Cevallics, they're the perissodactyls, or the odd-toed ungulates. And these include animals like the horses. So the upper Cevallics has animals like the one-toed horse Equus, 3-toed horses like the Hipparianines, a very diverse record of rhinos, including one of the largest to be found in South Asia. It's called Punjabitherium platyrhinum, and rhinoceros cevalensis. There was also the odd Chilicothera, which is a strange group of perissodactyls. They kind of looked like a mix between a sloth, a horse, and a gorilla. And of course, the proboscideans, which are probably the best represented in the Upper Cevallics. It's got a huge diversity of elephantids, which includes animals like Elephas hypsodorphus, the probable ancestor of the modern Asian elephant. Elephas platyfront, which was a smaller species occurring fairly early in the record. It was quite possibly the first elephantid in South Asia. And Elephas platycephalus, which is an enigmatic proboscidean, found fairly high up in the sequence near the town of Siswan in India. Stegodons are, again, quite diverse. You've got this incredible skull of Stegodon ganesa here at the Natural History Museum in London with 12-foot-long tusks. This was found by Baker in 1834. And the Stegodon insignis, which is a strange flat-headed elephant. And Stegodon bombifrons, Stegodon pingerensis. So you can imagine that there are lots of these things wandering around the Himalayan foreland basin between about 3.5 million years and 500,000 years ago. And of course, you've got a Gomphothera as well, Anancus cevalensis. So huge diversity of large mammals, almost continuous deposition from 3.5 million years to 500,000 years. It gives us an extraordinary ability to understand faunal change and how that's linked to environmental and climate change. When Falker and Cotley first found the Cevallic fossils, they called them tertiary Cevallics. They couldn't quite tell where they were in the tertiary sequence. It wasn't until Guy Pilgrim in the 1910s that we started to get a better understanding of the biostratigraphy of the Cevallic group. And he divided up the Cevallics into the upper, middle, and lower, and then further divided up the upper Cevallics into 2 biostratigraphic zones, the Tatrode faunal zone and the Pinjor faunal zone. And on top of the Pinjor faunal zone, you've got a conglomeratic layer called the boulder conglomerate, which is not particularly fossiliferous. It wasn't until the 70s, 80s, 90s, and 2000s that we started to do a lot of paleomagnetic work in the Cevallics. And this allowed us to actually put dates on the Tatrode faunal zone and the Pinjor faunal zone. So now we know that the Tatrode faunal zone extends from about 3.6 million years to about 2.5, and the Pinjor faunal zone extends from about 2.5 to about 500,000 years. The The formations in the upper Cevallics are difficult to define, and they don't trace well across the entire length and breadth of the upper Cevallics. I like to call the Pliocene sediments the pre-Pinjor sediments. This is an example of them. They consist of variegated clays and sandstones from near the village of Masol. The Pinjor Formation, which was defined in India, ranges from about 2.58 to about 500,000 years. I've got 1.77 to 500,000 years because of the boulder conglomerate, which is deposited in a time-transgressive manner from about 1.7 million years to 0.6 million years at different places in the Cevallics. The environment had changed by about 1.7 million years. There's probably a lot more uplift of the Himalayas, and this caused a lot of high velocity streams to flow down and deposit this conglomerate. And this wasn't an environment that was particularly conducive to fossilization, which is why we don't find much there. Now, people have been dividing up the Cevallics biostratigraphically for a long time. Pinjor divided it up into the Tatar faunal zone and the Pinjor faunal zone. Subsequent researchers have divided up, like the Harvard Cevallic group led by John Barry, into the Hexapterodon Cevallensis zone and the Elephas planifrons interval zone. And then other researchers have further subdivided the Pinjor into two zones, the Elephas Hysidricus zone and the Elephas Hysidricus crocuta, ursus, and panthera faunal zones. Now, the basis of biostratigraphic zonation schemes is faunal turnover. And because these biostratigraphic zones exist, there must have been some sort of faunal turnover taking place in the upper Cevallics. But it wasn't ever quantified properly. And that was sort of the focus of the work that I've been involved in for the last few years. So the question that I basically asked is, what are the characteristics of the faunal turnover in the upper Cevallics? To do this, I collected as many well-dated sites as I could find from the major fossiliferous localities in the Cevallic Hills and on the Potwar Plateau in Pakistan and in the Jammu Hills. And I had three kinds of data. So the first one, which is probably the best kind of data, are these stratigraphic columns with the sites mapped onto them, and each site has the various species that were collected from those sites. And then these stratigraphic columns are mapped onto paleomagnetic columns. Using this, you can actually get a fairly good estimate of how old these individual sites were. So that's one kind of data that I collected. The other kind was when you have a collection of sites around a section which was dated. The sites here are all around the village of Masol near the town of Chandigarh. And the Masol sediments were recently dated to about 2.8 to 2.6 million years. But because all of the rocks there are about Pliocene in age and are pretty close to the section which was dated, I assume that all of those sites fell in that age range. Now, I couldn't get a more precise time than 2.8 to 2.6 for these sites, but that was good enough for what I wanted to do. The third and the more challenging bit of data to collect was with these correlated stratigraphic sections. Now, every so often in the Cevallics, in the literature, you'll get a paper which will have a diagram that looks like this, where you have a litho column that corresponds to a particular formation. In this case, it's the Saketi formation from near the village of Saketi in northern India. And there's a whole bunch of species that were collected from this formation. However, in the paper that described this column, they didn't actually put a PMAG column along with it to give us an estimate of age. However, sometimes you get lucky and someone else has actually gone and mapped it, and we have a paleomagnetic column. For example, here, Azzaroli and Napoleon in 1982 went and mapped the Markanda Valley. And so we know that this section ranges in age from about 3.1 million years to about 2.7 or 2.8. So with some confidence, we can assign that age range to all these species that were collected in sites along that column. It's the best that we have, and that's what we get to work with. Thankfully, most of my data actually came from these sites, which I could correlate with finely resolved time bins. And I had about 5 stratigraphic columns where my data came from. Using all of this, I got an assemblage of about 61 mostly valid taxa. I call them mostly valid because I've got my taxonomic scheme for what I'm considering a valid taxa or not. And quite remarkably, from the approximately 200 sites or so that I collected, only 7 of the described valid species were not found in these columns. Unfortunately, I couldn't get a Calicopter or a giraffe in my sites. It's okay. One thing to note is that the taxonomy of the Stegodontids is a mess, and so is the taxonomy and the biostratigraphy of the cervids. So for the purposes of my analyses, I called all of the Stegodontids Stegodont Spo and all of the cervids Cervus Spo. Now, the way I measured turnover was by using metrics that are typically used by ecologists. And these are called faunal similarity or dissimilarity metrics. The way this works is you've got 2 bins, you've got bin A and bin B, and you want to know if the species in bin A are different from the species in bin B. Now, the differences can be caused by 2 processes. One of them is just a simple change in composition. If you have 10 species in bin A and 10 species in bin B, if those are completely different, then you have a complete compositional change between those bins. And these bins can be spatial bins or temporal bins. Another way you can get differences between these bins is if you have 10 species in bin A and 5 species in bin B, but all those 5 species in bin B are the same from bin A, then the only differences are caused by differences in species richness. Now, both of these processes combine to show you how these assemblages are different. So I took all of my sites and I binned them into 5 temporal bins based on the paleomagnetic timescale. The first 2 bins were in the Gauss-Kron. The first one was between 3.6 to about 3 million years. The second one was from about 3 to 2.6. The third one was in the earliest part of the Pleistocene from about 2.6 to 1.77. The fourth one was from the top of the Olduvai subchron from about 1.8 to about 1 million years. And the last time bin was at the topmost part of the sequence, so from about 1 million years to 500,000 years. My bins are roughly about 500,000 years to about 1 million years in age. And it's the best that I could do with the quality of data that I have. So I took my faunal lists and I calculated the Sorensen-Dice dissimilarity index, which can then be divided up into the composition change component and the richness difference component. And this is what we see. Between the first 2 time intervals, between the first 2 Pliocene bins, we see that most of the turnover is driven by composition change. That's reflected in Simpson's beta right here in the light gray. Between 2 and 3, most of the turnover again is caused by composition change, and a small portion of it is caused by differences in species richness between the 2 bins. But the pattern is completely flipped in the Pleistocene bin, so between T3 and T4, where most of the turnover or the differences between the bins is caused by differences in species richness. So this gives us a sense of some of the processes that are acting on these faunas and causing changes through time. But to get a more nuanced perspective, I looked at the pattern of faunal appearances and disappearances. And what we see is, between the first 2 time bins, the number of disappearances, it's about 12, equals the number of appearances in the subsequent time bin. That's why you get almost 100% of composition change. In the next 2 bins, you get about the same amount of species disappearing in the preceding bin and species appearing in the subsequent bin, but there is a difference in those numbers, which is what's manifesting as the difference in the species richness. And of course, This pattern changes completely when you look at time bins 3 and 4 and 4 and 5. So you're getting a lot of new species coming in the latest part of the Pliocene, and a lot of species disappearing which lived in the earliest in time bin 1. Again, in the earliest part of the Pleistocene, you're seeing more species coming in and species from the Pliocene going locally or globally extinct. But we know that the fossil record is notoriously incomplete, and an incompletely sampled can bias estimates of turnover. One way to get at how well these time bins were sampled is to calculate species accumulation curves. And what these curves are basically telling you is the rate by which you're sampling new species when you sample a new site. And what you ideally want are curves that are starting to flatten out. And what this means is that as you sample new sites, the rate at which you sample new species is going down, and it's almost becoming flat, which means you're pretty close to the true species richness of that site or of that assemblage, in this case of that time bin. Now, from my data, the first 3 time bins, the 2 Pliocene time bins and the first Pleistocene time bins, are fairly well sampled because these species accumulation curves have started to plateau out. But the other 2 Pleistocene time bins 4 and 5, they're not well sampled at all. And there are 2 reasons for this. The first one is the boulder conglomerate. It's not fossiliferous, and it gets laid down in a time transgressive manner from 1.7 million years, which is the base of time bin 4, all the way up to 0.6 million years, which is the end of time bin 5. So we have this entire chunk of unfossiliferous rock where the sampling is poor. The other reason sampling is poor because I only sampled sites and sections which could be dated. And so here's a map showing the Chandigarh area. Here's the town of Chandigarh. Here's the village of Masol. And this is the Patiali Rao section, which has been dated paleomagnetically. There are lots of similar sections to the west, which would also preserve the younger part of the sequence, which have never been dated. And so I didn't include them, which is why sampling is poor. It's poor because of natural processes like the boulder conglomerate. It's also poor because of the analytical techniques that I'm using here. So we're seeing this turnover take place, especially in the Pliocene and the early Pleistocene. But what's going on to the actual assemblage of species? The biggest thing that we see is a change in the taxonomic structure of these assemblages as you move from the Pliocene to the Pleistocene. And the biggest change occurs in the number of pigs to bovids. In the earliest Pliocene bin and time bin 1, between 3.6 and 3 million years, you actually have more species of pigs than you have of bovids. But as you move through time into the latest part of the Pliocene and into the earliest part of the Pleistocene, you see this spike in the diversity of bovids and a decline in the diversity of pigs, such that through time now, you consistently have this pattern where there are more bovids than suids. Most of the other taxa stay flat. The only other taxa that experience spikes in diversity are the cervids, but because there are so many complications associated with cervid taxonomy and biostratigraphy, I couldn't get a good handle on what that looks like. Okay, so we have turnover now after about 3 million years and about 2.5 million years. We know that there is a change in the taxonomic structure. Is any of this turnover being driven by environmental forcing? So what are the prominent environmental changes that are taking place at this period of time? The first thing is a gradual decrease in average temperatures and an increase in the fluctuation of climate. This is the benthic oxygen 18 stat from the Greenland ice core. And it's a proxy for ice volume, which is a proxy for temperature. And what you're seeing from the Pliocene into the Pleistocene, all the way up to the modern, is a general cooling and an increase in these fluctuations, showing that there are periods where it gets pretty pretty cold, and there are periods where it gets pretty warm. The other proxy that I looked at was lithogenic grain size, which is a proxy for monsoon intensity. And we see a similar pattern where monsoon intensity starts to decrease through time. And what this implies is that there's a progressive cooling and aridification through time from the Pliocene into the Pleistocene. This makes sense because you're seeing massive ice sheets in the northern hemisphere and in Antarctica, and the world is generally oscillating between cool and warm periods, trending towards cooler temperatures on average. Now, if that's the case, then we would expect to see more forested environments when it's warmer and wetter, and more open savanna or woodland environments when it's cooler and drier or more seasonal. And the animals that live in these two environments are slightly different, especially the herbivores. Now, herbivores feed on the plants, and with this environmental change, the plant community also changes, and so does the herbivore community that depends on those plants. Animals that feed on grass, or at least are more capable of ingesting grass, tend to be hypsodont. And what that means is that they have relatively high crown teeth compared to the width of the crown. You've got other kinds of species called brachydont, which have relatively short crowns. These are animals like pigs or hippos or us. And then you've got mesodonts, which have teeth sort of intermediate between brachydonts and hypsodont species. And these tend to be mixed feeders. So if the environment is causing faunal turnover, we would expect to see more hypsodont taxa in our assemblages. So what I did was I looked at the teeth of all of these animals by going and sampling specimens in a variety of museum collections. And I scored them. If they were hypsodont, I gave them a score of 3. If they were mesodont, I gave them a score of 2. And if they were brachydont, I gave them a score of 1. And what we see through time, looking at the average hypsodonty scores of these assemblages, is that the first time bin, which is the first Pliocene bin, has an average hypsodonty of about 1.6, suggesting that there are more taxa that are better adapted to a browsing or a mixed feeding lifestyle. But as you move through time, the average hypsodonty score increases, suggesting that you're getting more high-crowned taxa showing up. This is actually reflected in the appearances that we see in record. So just focusing on the time bins that are well sampled and the taxa that appear, we can see that the average hypsodonty score for the taxa that appear is about 2.4, but the average hypsodonty score for the taxa that disappear or go extinct is about 1.9. So the taxa that come in new as the climate is changing have higher crown teeth on average, and therefore are better adapted for these more open environments. And the taxa that disappear are these animals with brachydont dentition, low crown teeth, perhaps not as well suited for these open habitats. Where are these animals coming in from? Well, with these climate changes and fluctuations in sea levels, land bridges form between America and Eurasia, and one-toed horses disperse over sometime before 2.6. It's about 2.7 to 2.6 when horses first show up in the Cevallics. Deer disperse down from Western Eurasia. Giraffes and elephantids disperse in from Africa, and stegodontids disperse in from Southeast Asia. The endemic fauna typically includes animals like rhinos, bovids, and suids. So just to recap very briefly before I move on to the next section of this talk, we see a major turnover after about 3 million years and 0.6 million years. We have poor sampling after about 1.77 million years that obscures any real patterns in faunal turnover. There's a major shift in the ratio of bovids to suids from the Pliocene to the Pleistocene. So there's a major restructuring, at least of the taxonomic composition of these assemblages as we move from the Pliocene to the Pleistocene. And this turnover seems to be environmentally forced, as evidenced by the change in tooth morphotypes that we're seeing through the section. And lastly, this turnover is driven by both immigration and extirpation and extinction, as evidenced by the fact that a lot of this turnover manifests as just composition change, but not a lot of simple changes in species richness. It's not just new species coming in or species going locally extinct. It's a combination of the two. All right. So the next part of this talk is going to be focused on how this turnover is linked to the modern herbivore guild. And a guild is basically just a collection of similar animals doing similar things. So the herbivore guild is basically animals which eat plants. One way to look at this is to look at the size structure. The size structure is basically a frequency distribution of the body weights of the different animals that you see in these different assemblages. And for the most part, from the late Pliocene to the earliest part of the Pleistocene, we don't actually see significant differences in the size structure. And turns out these similarities translate all the way up in the section to the late Middle Pleistocene and the late Pleistocene as well, where you get these normally shaped size distributions, suggesting that the proportions of small herbivores to medium-sized herbivores to large herbivores stays about the same in these ecosystems. The only change that you're seeing is within these groups. So structurally, the herbivore guild is staying about the same. And if you look at the taxonomic composition of late Pleistocene assemblages, basically from about 50,000 years to the present, you're seeing lots of elephants, bovids, deer, hippos, rhinos, horses, and pigs. Pretty much what you find in these early Pleistocene assemblages as well, and even in these late Pliocene assemblages. But the one difference to note is that there are actually more species and there's a lot more diversity in the Plio-Pleistocene than there is in the late Pleistocene. And that's actually evidenced by the total number of species. There are about 25 species in the earliest Pleistocene, about 28 in the latest Pliocene. This number is actually much higher because I've not included the cervids or the stegodontids as individual taxa, but just as stegodontspo or cervispo. And the number of species in the late Pleistocene is actually quite a bit lower. And we see this extinction manifesting across a wide range of mammals. Basically, we lose giraffes, we lose camels, we lose a lot of the big buffalo and antelope, you lose most of the big pigs, you lose a lot of the diversity in rhinos, you lose anthracotheres. You get a few new species coming in the Middle Pleistocene, animals like Paleoloxodon, which is a giant proboscidean. Muntjacs come in fairly late, but beyond that, a lot of the other lineages that are found in early Pleistocene are still found in the middle and late Pleistocene. We just see a loss of a lot of these species. This turnover takes place sometime between about 1 million years and 200,000 years ago, but we just don't have the fossil records to understand the nuances of this turnover or figure out why it's actually taking place. And interestingly, even though we're seeing this decrease in diversity in total richness of the herbivore guild, the actual taxonomic structure stays pretty much constant from the late Pliocene all the way to the modern, where we see ecosystems that are dominated by bovids and only have. So we see this change taking place after about 3 million years, and then this taxonomic pattern that we see stays fairly constant. There's a lot more cervids. There are a lot more cervids in these modern South Asian ecosystems as well. But the story doesn't end there, because if you think about any modern South Asian assemblage, if you go to a national park in India, let's say Kaziranga in Assam, you aren't going to see 3 species of elephant. You're only going to see 1. You aren't going to see hippos in the Narmada or the Godavari anymore, and you're not going to see zebra galloping across the South Asian landscape. So the story of the herbivore guild actually continues on into the modern with the recent megafaunal extinctions, which took place between about 30,000 and 8,000 years ago, with the extinction of a lot of the proboscidean fauna and the hippos and the equids. We actually see a lot of lineages which had their origin in South Asia back in the Pliocene go extinct in the blink of an eye at the end of the Pleistocene and the beginning of the Holocene. We lose Paleoloxodon pneumaticus, which is one of the biggest elephants to have ever lived. We lose Stegodon pneumaticus, which is one of this extremely diverse lineage of roof-toothed elephants. The Indian zebra, Equus pneumaticus, which is related to the Cevallic horse, Equus cevallensis, also goes extinct. Hexaprotodon, which is probably from the same lineage as Hexaprotodon cevallensis in the Cevallics, goes extinct actually right in the beginning of the Holocene. And Bos pneumaticus, the Indian auroch, it's a pseudo-extinction because it survives today in the form of the modern domestic Zemu cattle. There were also ostriches in the late Pleistocene of India, which go extinct quite late in the earliest part of the Holocene. And what all of this tells us is that the story of the modern day herbivore guild in the Cevallics actually starts all the way back in the late Pliocene, when a lot of the modern components, animals like deer, animals like elephants, immigrate in from other parts of the world and replace a lot of the endemic animals like pigs and native bovids. And this story is a story of continuous immigration and extinction all the way from about 3 million years, all the way up to the modern day with the megafaunal extinction. And so what these Plio-Pleistocene assemblages in the Cevallics tell us is the story of how this herbivore guild assembled, what the different processes were by which animals like cervids or bovids came into the subcontinent or evolved there. And so I think I'm going to stop there, and I will take any questions that you might have. Thank you very much for listening.
Jukar, you can close the slide share mode.
Yeah. So thank you very much, Advait, for your presentation, and I think we can open it up for questions and see if what we hear here.
Yes, we have Catherine Beji. Please open your
mic. Sure. Can you hear me?
Yeah. Go ahead.
Okay, great. Thank you. Thanks very much. So trying to keep track of all the different changes in the faunas, I'm wondering with the modern fauna that you have, how much of the new arrivals are endemic as opposed to immigrants? I'm just curious about that balance.
So at the genus level, the rhinos are endemic. The horses, well, of course, come from North America, but the local Indian radiation seems to be an endemic radiation. It's unclear what the cervids are doing. I think Roman Kreuter has gone and redone some of the taxonomy. So a lot of the extant genera, which you find in India, seem to be there in the earliest part of the Pleistocene. Animals like Rucervus, Rusa, there might even be an Eld's deer there. So those things are endemic. The Elephas, which comes in quite late at about 2.7, Elephas hyatsutricus seems to radiate out into Elephas maximus, and of course the hippos represent an endemic lineage. There are some animals like muntjacs, which I think are coming in from Southeast Asia. But yeah, I think some of the bovids are endemic. It's hard to know because we don't have a lot of good dates on these bovids across the old world. And because of a lot of issues with taxonomy, it's hard to know if some of these animals are the same in China or in the Middle East, and so doing any kind of phylogeography gets a little complicated. What I would love to have is a sequence from the early to the Middle Pleistocene in peninsular India to see if there are any endemics which are then dispersing up. I think it's just a matter of time before we find stuff.
So, well, that raises the question, and this can be a simple answer and not a long one. Are there sites in peninsular India that will contribute to these analyses?
None that I know of right now. There's the Ghansi Formation in the Narmada Valley, which is supposed to be late early Pleistocene to middle Pleistocene in age. There aren't a lot of fossils known from there, but it's a good place to start.
Thank you.
Mm-hmm. Okay.
Hi. Yeah, thanks. This really fun talk, even though I've heard parts of it before, but it keeps evolving. So it just gets better. The similar timing of what happens between pigs and bovids in East Africa and Southeast Asia is really fascinating.
Yep.
They're different species, but some of the same genera. But, you know, it's like, what's going on with this trade-off between suid-dominated and bovid-dominated, at least between those two groups? Do you have any speculations or thoughts about that?
My best guess for that is that you're losing out on a lot of low-lying vegetation that suids use to breed in. You're losing a lot of sort of low-level shrubbery, and the mixed feeders which are coming in, things like cervids, at least in India, are going after some of the same vegetation types that the suids might have gone for. Besides that, I'm not sure. We actually do see quite a bit of turnover in the suid lineages themselves. So in the early Pleistocene, we do have, I think, 4 suids, and then that trickles down to 2. You've got sus and porcula in the modern day. So something is going on in the Middle Pleistocene where the overall diversity of suids is declining even more.
What are the carnivores?
So the record is not that great, but from what we know, there's a Pantherine cat. It's probably Panthera. I'm not pronounce the species name to save my life. It starts with a G. It's like a jaguar. There are hyenas. There's an Agriotherium, which is a big bear, which is also what you find in East Africa. So a lot of these faunas seem to be fairly similar. There's a Macarodontine in there as well.
Okay, thanks.
Mm-hmm.
We have Professor Rajiv Patnaik. Please open your mic.
Hi, Advait. Can you hear me?
Hey, Rajiv. Yeah, go ahead.
Great. It was very nice to brush off my knowledge. I have two questions. One is about the Punjabi therium you said.
Mm-hmm.
Earlier workers, I guess Khan or somebody reported it as Coelodonta, if I remember.
Right.
Is it any way related to Punjabi therium? Is related to Coelodonta? Do you think?
So that name has gone through a variety of different changes. It was originally described as Rhinoceros platyrhinus by Falconer and Cotley. Then it changed to Punjabitherium because Ehsanullah Khan described a new specimen, and he said that it's not rhinoceros, it's actually Punjabitherium. So all of that became Punjabitherium. And then Luca Pandolfi went and reclassified it as rhinoceros. So right now, the most recent phylogenetic analysis places its sister to rhinoceros. So that's where we are right now. I think Coelodonta evolves on the Tibetan plateau and is related to things like Dicerorhinus, which is like it's a northern Chinese radiation. But whatever's going on in South Asia is very similar to what's going on in southern China as well, because you have a rhinoceros there.
Right. Thank you. The other
And
other
holotype.
question is about, pardon?
And you've got the holotype in your collection of Punjabitherian.
Oh yes, oh yes, oh yes, oh yes. Uh, the I have worked in Jhansi area, and just to inform you that we have found just one tooth of likely of it, so not yet anything which would be very exciting. So I heard about this paper by Datta on lion specimens from Bankura. Do you have any update on that, or Datta 1976, I guess? Yeah.
I'm familiar with that paper. Okay, so the problem with Bankura is that we have no dates on those fossils. It's really hard to tell if anything is a lion or a tiger based on anything that is not a complete skull, because you have to go by suture marks on the skull to actually distinguish between the two species. Based on molecular data, Panthera tigris splits from the Southeast Asian subspecies of tigers by about 50,000 years, and that's when we think it shows up in the Indian subcontinent. Lions, at least the modern genomic groups of lions, are basically the same as the Barbary lion in North Africa, and they show up at about 38,000 years, or at least that's the genetic split. So we can get some radiocarbon dates on the Bankura specimens, but it's still unclear. There are also all kinds of strange things coming out of Bankura. I think there was a giraffid reported from there. There was a crocuta, which is not known in any of the other peninsular sites. So it could be just a different Pantherine cat from the early to middle Pleistocene when we have giraffids and some of these other groups. But I think more work needs to be done on those faunas.
Excellent. Well, thank you, Advait.
Yeah, thanks for the question. Bob?
So Advait, I'm particularly interested in the processes that permit the biogeographic dispersal of different types of animals, and I'm wondering. I of course love that diagram you have with the horses coming in from North America and other elements coming in from Eurasia and perhaps also Africa. And I'm curious, are you and your colleagues starting to develop an understanding of the corridors of habitability that must have allowed these animals to wander into the subcontinent? And what is that research looking like?
Yeah, so a lot of that started off with taxonomic reassessments, and some of the work that I've done with Ray Bernor has looked at these three-toed horses in the subcontinent, and we found Chinese lineages and African lineages in the Pliocene. And it's interesting because it implies some sort of open habitat corridor from East Africa into South Asia and from China into South Asia as well. But based on faunal similarity analyses between Pliocene sites in Yunnan and the Cevallics, we think the most likely routes were from the north, from north of the Tibetan Plateau across the steppe and then south through Afghanistan, or even across from Turkey to Iran and then into India. There doesn't seem to be a lot of faunal connections between Southeast Asia and the Cevallics just because of the differences in habitats. But actually, Rajiv and I have a paper which I just submitted on a Pleistocene Gomphothere from Kashmir. So there's a cynomastodon which is typically found in northern China, South and Southeast Asia, and even Burma, but it was never found in India, and we actually are describing a specimen from an intermontane basin fairly high up in the section. So there has to be some sort of a forested or semi-forested corridor from southern China in the Pleistocene, which has allowed some of these animals to come through.
Yeah, I think that points out the extraordinary challenge that you have as as interpreting the rock record and the paleogeographic and geomorphic record from the faunas, and it comes back to taphonomy, of course, which Kay has championed through the years, and this challenge of trying to tease out these stories with the limited data. And for example, we had a talk a little bit ago. Parth talked about the hominid record, which is so extraordinarily sparse in the subcontinent, and yet, presumably there were hominids of various kinds on the landscape, but they just are not yet found in the rock record. And so, it's an amazing challenge of sort of crime scene reconstruction or CSI kind of work to try to piece these stories together based on both the biogeography and then the capacity for these animals to be recorded in the rock record and then found as fossils.
Yeah, I mean, it's all a probability game, right? What are the odds that an animal dies in a place that it turns into a fossil? What are the odds that that part of the section gets exposed? What are the odds that I'm going to be walking on that section to go and collect it? So, it seems like fairly improbable events, but if you put in enough of a search effort, improbable events become quite probable.
Well, and following up on that, I'm curious just to hear your thoughts on targeted research. And over the next few years, if you were to wave a magic wand, I think you did mention a couple of places where you're interested in getting additional data, but would you think that there could be sort of strategically targeted collecting done in the Cevallics that would help answer some of the questions that you're posing?
Oh, for sure. One of the biggest challenges of the Upper Cevallics is that a lot of the holotypes were found in the 1830s and 40s and weren't tied to any localities. So we need to actually go to these dated stratigraphic sections and collect as much as we can, kind of like what the Harvard team did, except they got fresh PMAG data, and then see if we can actually figure out what these species are and get a better understanding of the true stratigraphic range of these taxa. There's also a desperate need for taxonomic reevaluation of a lot of these species. There are lots of wastebaskets in the Upper Cevallics, problems that started with Falconer and Cotley that were perpetuated by Osborne, and then they just kind of spread through after that. And so, I mean, the stegodons are a classic case of this. Falconer and Cotley named Stegodon ganesa and insignis presumably on teeth, but they have very distinct skulls. It's actually unclear what teeth he was comparing, but he said that these teeth are indistinguishable, even though the skulls are quite different. So they must belong to sexually dimorphic forms. Osborne took this idea and went on with it and coined a new term called Stegodon insignis ganesa, which is taxonomic heresy. You can't actually do that. You have to make one a junior synonym of the other. But because of that, any stegodontid tooth that was found in the Plio-Pleistocene was either called Stegodon insignis, Stegodon ganesa, or Stegodon insignis ganesa. And so it's almost impossible to tell what species you have in the sequence because of that. So we need to go back to the basics for a lot of these species.
Thank you.
Mm-hmm. And Kay's got a question.
Yeah, this is another kind of tangent, but with these fossils occurring, on the surface, is there any evidence that people earlier, the Mongols or any of the other earlier people that civilized this part of the world collected or recognized these as objects of interest?
Yes, there are actually a few records of this. So Firishta, who was a historian, wrote the history of Muhammadan rule in the subcontinent. And he writes about the reign of Firoz Shah Tughlaq. I forget what year he ruled the Delhi Sultanate. But there is a report of Firoz Shah's army going through the town of Ropar and digging a canal through a mound where they found bones that they thought were the bones of giants. And we know that Roper is in the upper Cevallics, so they're probably finding chunks of elephant or Cevatherium or something of the sort, but they're calling bones of giants. Now, Baker and Durand got their first hints at where these fossils were because the Raja of the town of Nahan gave them a tooth which was called a Deoke heart, which basically translates to a god's bone, and then told them where they found this tooth. It was a tooth of Ugampather. And so there have been sporadic accounts of local Indians finding fossils and assigning some kind of meaning to them. But it's not as well known as in some other places, perhaps.
Okay, thanks.
Mm-hmm. Catherine?
Yeah, I have an ecological question. In your view, what are some of the, say, Middle Pleistocene and Late Pliocene faunas similar to, if anywhere, in the world today? Now, I realize that they're very different because of the large number of mega herbivores that are no longer with us. But in terms of, say, proportions of suids and bovids, or the suid-bovid-cervid combination, are you seeing, say, Southeast Asian faunas in any places, or Bornean faunas, or is there nothing that is ecologically similar?
East Africa. I think I've got like a 33% generic similarity between the early Pleistocene and Pliocene faunas with those from the Turkana Basin. If you go to the level of tribes for the bovids, the similarity goes up even more. I think part of the issue is that people were naming things based on the place that they were found, and I bet that a lot of these things are actually from the same genus, just things that have dispersed over. But compositionally, I think what we have in South Asia is very similar to the savannah faunas in East Africa.
So not anything like then the forest faunas of Southeast Asia?
No, so we don't have any evidence of the Gigantopithecus cynomastodon fauna in South Asia. I think the Cevallics are very much a savanna ecosystem, at least in the Pleistocene. Mm-hmm. What you're seeing in southern China and in Southeast Asia is a more close canopy forest fauna.
Right.
Every so often you'll get elements of that in the Cevallics, things like cynomastodon, but we have no evidence of Gigantopithecus after the Miocene. So none of these large pongids are there. None of the other taxa that you typically find even in Burma up there. There's a lot more similarity in the Miocene, but not so much in the Pleistocene. I think things are getting a lot more provincial. And at some point in the future, I'll go and test how provinciality between Southeast Asia, South Asia, East Africa, and China.
Thank you.
Mm-hmm.
I've got a quick question on the megafauna story. Here in North America, we ascribe the loss of megafauna, or we notice that the loss of megafauna is tied to the arrival of humans. Mm-hmm. And that's been postulated by many to be a cause and effect. And is there any? Do you see any kind of a linkage between faunal extinction and the potential advent of hunters, of human hunters?
Yeah, so the India story is really interesting. Based on the dates that we have, which are not great, but they're the best available dates, the extinctions take place about 30,000 years after the arrival of the 60,000 year Homo sapien wave. If Homo sapiens are in the subcontinent by about 100,000 years, we've got a 60,000 year time lag between the extinctions and the arrival of Homo sapiens. The interesting thing is that the extinctions all start after microliths become common in the archaeological record. And these microliths, we think, were used as projectile points. So humans are getting more sophisticated with their technology by about 45 to 35,000 years, and the extinctions all take place after that. Now, the interesting thing about South Asia is that we have a fairly low magnitude of extinction. Only about 4% of the large of the fauna goes extinct. which is very similar to what we see in parts of Eastern Africa and Southern Africa. And the reason for that might be co-evolution, the idea that these lineages of megafauna evolved with our ancestors and therefore had adapted to whatever people are doing on the landscape, if it's habitat change, if it's hunting, if it's something else. And we have quite a diverse lithic record in the Indian subcontinent. I think the oldest well-dated tools in India go back to about 1.7 million years in South India, and they're Acheulean tools. And then we have a variety of different tool technologies. We've got the Narmada hominin cranium, which if you look at the phylogenetic analysis in the new Harbin cranium paper, places it just stem to this group of like Homo daliensis or longi, whatever you want to call it, and Homo sapiens. So there are multiple species in the subcontinent doing lots of different things. We don't have a lot of kill sites, but kill sites are rare to begin with, and the probability of finding them further back in the record gets even worse. So long story short, I think people had something to do with it. I think the correlation is pretty strong, but the Indian story is still evolving. I think we need to get a lot more data to get a true sense of the extinction magnitude. However, all of the things that survive into the late Pleistocene were also found in the middle Pleistocene. So they've gone through lots of climatic changes, but they only blink out in the last 30,000 years.
Right. We see that as well here in North America. Well, wonderful. I'm looking for any other questions. I think that we've had it's an interesting, again, an interesting story to piece together. And I think that what I enjoy about this partly is the opportunity for future targeted research, and particularly as we get a better and better handle on the age of the rocks through paleomagnetic stratigraphy primarily. I think we're going to be in a position to do targeted paleontological collecting, which traditionally we've gone out to look for a fossil, but now we're going to be walking in strata of a certain age, looking for a certain type of fauna, and I think that that's an exciting prospect for your discipline, and I'm super excited about the ability for us to date the rocks, which is really as you wander around the entire world, some of the best dated sedimentary rocks in the world are in the Cevallics, in the foothills of the Himalayas, because of the record of paleomagnetism together with some volcanic ashes. So there's a super synergy here between the stratigraphic world and the paleoecological and paleontological world, and I think that's a great thing to celebrate. But I'd like to thank you, Advait, for your talk this morning, and I'd like to encourage all of us to come together for our last seminar a week from today, and we will have some kind of a wrap-up session. We haven't completely assembled how it's going to happen, but if you come a week from today, we'll have a synthesis of the presentations that we've had over the course of the last couple of months. So. Mukhtar, do you have anything further to say?
No, it's okay. And thank you very much for Advait and for participating and presenting.
So Mukhtar did offer the possibility, we were discussing a few minutes ago about we might have some kind of a questionnaire we might circulate, just so you can be thinking about it in terms of what future programming might be of interest to people. There might be some kind of a Google Doc of some kind that would circulate, and people could offer suggestions and volunteer topics or features for a future seminar series. And so I think one of the things that's been proven through our work here is that this is a possible format, and once we've got the ropes figured out, Microsoft Teams works really well, and we're able to bring people together from across the face of the earth to join in a common discussion, some of it in the middle of the night, some of it in the morning, and it's been great fun. So we'll look forward to having some discussion about that in our seminar next week. But thank you all for participating this evening, and thank you again, Advait, for your presentation.
Thank you so much.
Thank you. Thank you.
Thank you all.